Welcome back to 2141 Tuesday, week 2. Yes, quiz before we start. By the way, if you don't remember, I'm Noni. If you weren't here last week and you still need a course outline, please shut up. Please shut up. Thank you. If you never grabbed the course outline from last week, please come and see me during the break. I'll give you one. We said the quizzes will open every Tuesday at 9. Today is Tuesday, 9 has passed and the quiz is not there. Reason for that, we had a slight technical difficulty. The quiz should open sometimes after this lecture. So it will open this afternoon. With the quizzes, you should be able to see a link for Moodle. It will be at the top. It'll say Quiz 1 Number Systems. And once you click it, the way it's going to work, there will be a new window. No, that will probably be the same window. You're going to have another button. It's a bit of a process. It's a straightforward process, but there will be another button that says Run Tutorial. The reason why it says Run Tutorial rather than a quiz is because it's implemented on a system that's called Adaptive E-Learning Tutorials. It's a new system that we're trialing. And they call those things tutorials rather than quizzes. You click Run Tutorial, then you're going to have a new window opening, loading flash animation and whatnot, and your quiz will come up. Now, few things you must know about the quiz. Please don't come complaining that you didn't know it afterwards. Number one, there's no time limit for the quiz. You can start it. You can take all the time in the world to finish it. You can potentially, I have to verify it, but I'm pretty sure you can even close the quiz, close the window midway, come back 2 days later, reopen the browser, click the quiz, and it will take you back to where you were. It will remember your session. That's one thing. The other thing, very important, you cannot backtrack questions. You can only go forward. Once you click next, that's it. You can't go back to the question. So overall, there's 10 questions, by the way. Fairly short questions, by the way. Nothing to panic about. There are going to be 10 questions. You see the question, you answer it, you click next, you move on to the next question. Please don't tell me that you accidentally click next or accidentally something happened, because I'm telling you now, you cannot backtrack questions. Number 3, which is very obvious, and I mentioned it before, don't copy from each other. You're all getting the same quiz. Please shut up, it's important information. You're all getting the same quiz. It's important you do it yourself. Please, after you've done the quiz, don't go and tell your friends what was in the quiz or what sort of questions or anything about the quiz. And on the same token, don't ask your friends who have done it before. We do have ways to know... Shut up, please. We do have ways to know if you've done it together, and as I said, because it's so easy to copy in the quizzes, penalties will be severe. It's an instant failure of the course. So you'll still get your mark, but you will have a fail next to it, and you will have to repeat the course next year. I hate threatening, but please don't try me on this one. The quizzes are really there to get you to progress through the course, so you don't just sit through the lectures and then half an hour before the final exam start studying. So it sort of forces you to go through it. Quizzes are not hard, they're not long, but they will make sure that you know what's going on. If you can't be bothered learning anything, just guess the answers. It's better than not doing it at all. Huh? No, they're not multiple choice. There will be some multiple choice questions, not all of them. Some of the quizzes, what I said, are developed on this adaptive e-learning tutorial. Some of them will be interactive when you drag and drop things and move things around and do fun activities. Not all of them are like this. We're progressively developing more and more of them, but it takes time for each quiz. Just one second. Some of them are still going to be multiple choice. Some of them will be short answers. Some of them will be interactive. Yeah.
I assume all the quizzes are auto-marked?
Of course. Auto-marked by me. Some are, some aren't. I do keep an eye on answers. So short answers, if for some reason my automatic marking program missed out on something, I will pick it up. I do keep an eye on your answers and what's going on. As I said, nothing to worry about. If you do have questions, if you find bugs in the quiz, as I say, it's a new system. If you find bugs, email me straight away. We can fix it. I've got people working on it. It's not a problem. Nothing is intentional. It's all for your benefit, and we're here to help. Any other questions on the quiz before we continue? By the way, the quiz will be open until Monday 9 a.m. You won't be able to access it after Monday at 9. And that's when we will also release your marks. You won't see your marks as you're doing it. All the marks will be released Monday 9 a.m. After which you won't be able to do the quiz. I don't care how much you beg. Yeah?
Would we know if will it completely say whether you got the question right or wrong, or will it just go on?
I'll let you know. I need to check how we're going to do it. Ideally, I would like you to know which questions you got wrong, obviously, and then know.
Like straight away through the quiz.
Not at this one, but maybe in further quizzes. There's other cool features I'm trying to put into the quizzes as I go along. There's only so many hours in a day that I can have. But you probably find that as we go with the quizzes, you're going to find things like more informative feedback about your questions as you go along. Maybe we'll shove in some videos here and there, but we'll see how it goes. Any other questions on the quiz or anything else before we start the lecture today? No? Okay. So what did we do last week? Last week we talked about digital systems. I introduced very high level of digital systems, a little bit abstract at times. We started talking about number systems. We said what are positional number systems. We generalized our decimal number system and how it's part of like a bigger system of number systems. We said how you can really do mathematics and arithmetics in any basis, and that we chose base 10 probably because we have 10 fingers and it's easy for us to use. But then we said how we convert between bases. Most importantly, between binary and decimal and hexadecimal and octal, which are the bases we'll use mostly. Now what we'll do today, we'll start introducing combinational logic circuits. We'll learn about Boolean variables and Boolean algebra. We'll learn about logic gates and how to manipulate Boolean equations. So let's get with it. So what are binary variables? Binary variables are the variables which we'll be working with. By definition, a binary variable can take one of two values, the 0 and the 1, which we said we use a lot in digital. And we will express those variables either by letters of the alphabet, such as A, B, C, sometimes X, Y, and Z. Usually you'll see either a lot of A, B, C, D, or W, X, Y, and Z. These are the most common ones, but there's no problem using any letter of the alphabet. A bit later in the course, we'll actually give them some more meaningful names. So we can either give them letter names or more meaningful names such as X1, not very meaningful. But then things like CLK stands for clock. You might see a variable called EN for enable. Things like reset, when we'll talk about a reset signal coming into a circuit, and so on. So binary variables, either one letter or few letters, either way. Now, in Boolean logic, there's three main logical operators that are making the basis of all the Boolean algebra and logic operations. These are the AND, the OR, and the NOT. Now, the AND operation is denoted either by a dot, similar to multiplication, or sometimes we will not put any notation between two variables. So it's very similar to mathematical multiplication. The OR operation will be noted by a plus sign. And that will denote one variable or the other. And we'll show what they do. The not operation will be denoted by an overbar above a variable. So as an example, not x. You might see it sometimes denoted by an apostrophe after the, or a dash after the variable. So that will mean not x as well. Sometimes you'll see a squiggle. That means not x. In fact, there's many ways. Sometimes you might see a slash, that's a not x as well, or a backslash. Sometimes an exclamation mark. So there's all these different ways you can express a not operation. We will mostly use the overbar in this course. That's my preference for notation. Some other books prefer the dash notation. They all have their pros and cons, by the way. Now, with the operations, I talked about the and the or. They're what we called binary operations. And not because they work on binary variables, but rather binary from the word by to work with two things. So we might have x and y, or x or y. So the operation always takes two arguments or two operands and do the operation on them. The not operation is a unary operation. It only takes one variable and work on it. So there's only not x, so only one operand. Just to be a bit more to correlate it to mathematics, things that are binary operations are multiplication. You multiply two numbers. Things like modulo. Operation, you take 5 modulo 2. That's an operation that runs in two variables or two numbers. Things that are unary operations are things like the minus sign. So you might have things like minus 5. You know, the number minus 5 is really just 5 with a unary operation beforehand. Or the factorial operation, you know, 8 factorial, another unary operation. So we have both the and the or binary operations, no is a unary operation. As I said before, with the and we can omit the dot if the context is clear, and we can say things like have an expression z equals x and y. So we either write it with the dot or with no dot if it doesn't cause any confusion. Similarly, if you want to know the or operation, we can say things like z equals x or y. And just for completion, z equals not x. Now, what I never, ever, ever want to hear from you is things like z equals x plus y, or z equals x times y. It's not plus and it's not times. It's or and it's an and. Just be careful. I might slip myself every once in a while because it's very easy to mix them. But the correct way to pronounce them, x or y, x and y. If you think about it, and you'll see once we actually introduce what they're doing, you'll see that they are very close to base 10 addition and multiplication in base 2, but they're not quite there. So that's where the symbols come from. So what do those operations do? Each one of them takes two variables. Well, the and the or takes two variables or two constants. They can either be a 0 or 1. And they're defined as such. So 0 and 0 will be a 0. 0 and 1 will be a 0. 1 and 0 will be a 0. 1 and 1 will give us a 1. So you can think about it as it's 0 when at least one of them is 0. It's only 1 when both of them are 1. Then we have the OR operation that is defined. 0, 0 is 0, 0, 1 is a 1, 1 over 0 is a 1, 1 over 1 is a 1. So the OR operation will be defined as it's 0 if both of them are 0, or it's a 1 if at least one of them is a 1. I think the NOT operation is fairly obvious. You have NOT 0 will be a 1, NOT 1 will be a 0. So we take the value, we negate it. Very easy for now. Now what I wrote in this form here, the definitions, we can also tabulate it in a truth table. And truth tables are stuff that we are, the tables that we will use quite extensively in this course. Truth tables is a way to list all the possible combinations that variables can take, and then show what value a function would take working on those different combinations. So if I want to express my 3 operations in form of the truth table, I will write out my variables, and I will list all the possible combinations. In this case, with 2 variables, I can only have 4 different combinations, and I'll do the operations on them. So the AND operation, just from what we've seen before, if we have at least one 0, we'll end up with a 0. We have both 1 being a 1. The OR operation, if at least one of them is a 1, we'll get a 1. And the NOT operation, as before. Now that's fairly easy to work with when we have 2 variables. There's only 4 different combinations we can produce. And usually we write them in a binary counting order. So 0, 1, 2, and 3. Sometimes we might actually want to write them in a gray code order. It will become more apparent later why we would want to do this. But we don't have to. I mean, you can write it in any order that you want, as long as you cover all the possible combinations there are. But now, if we're going to go to more than 2 variables, 3, 4 variables, then it might not be so simple to come up with a truth table. For example, take if we had 4 variables, w, x, y, and z. What's a nice, easy way to come up with a truth table that will cover all the combinations? Well, if you know how to count in binary off the top of your head, you just write 0, 0, 0, 0, 0, 0, 0, 1, then 2, 3, 4, and so on until we get to 15 in binary. Another quick way of doing this is to go column by column, starting with the least significant bit. So I'll start with column Z, and I'll just alternate between 0, 1, 0, 1. 0, 1. Then I'll go to the next significant column, and I fill it up alternating, but now I'll have 2 zeros, 2 ones. 0, 0, 1, 1. On the same logic, I'll continue to the next significant column, and I'll have 4 zeros and 4 ones. And obviously, then 8 zeros and 8 ones. Now, if you read each line, you'll realize that we just wrote a counting order in binary. So the first one corresponds to decimal 0, then 1, bless you, 2, 3, 4, 5, 6, 7, and so on until we get to 15. So if you don't remember how to count in binary, that's a good way of producing a truth table, and then you're sure that you actually cover all the different combinations. Now usually in a truth table, these will be possibly our input variables to some system, that there will be some function f that will work on these variables and produce some sort of result. So f, just throwing an example, could be getting the values 1, 0, 1, 0, 1. For no apparent reasons why I chose these combinations of zeros and ones, it's just an example of a function. Now my function might say that whenever w is 1, x is 1, y is 0, and z is 0, the function should produce a 0, as an example. We will see how to come up with those kind of functions a bit later. Any questions so far? Fairly simple. You know who was really interested in those kind of logic tables and Boolean algebra and so on and so on? This guy? You were going to say that? Do you know who this guy is? Huh? De Morgan? No, that's not De Morgan. De Morgan looked nothing like this. No, it's this guy. Yeah? Ring any bells? Yeah? One of the greatest mathematicians, no? You know, he came up with theories like this. No? Yeah? Come on! Yeah, it's us.
Imaginary numbers.
Huh?
He hates imaginary numbers.
He hates imaginary numbers. Clearly. Lewis Carroll was his pen name. His real name was Charles. He couldn't, by the way, pronounce his own name either because he was stuttering a bit. In fact, they said he was stuttering only when talking to adults. Not so much. He talked quite fluently with children. Anyone seen The King's Speech here? Yeah. I actually haven't seen it, but they told me that apparently, no, I haven't seen it. But apparently you only stutter when you talk to other people, but if you talk to your cat or to your carpet, you're fine. Apparently it's true. I don't know. Anyway, let me tell you what information I could dig up about this Lewis Carroll, because he's actually quite a fascinating character. Just so you know, first of all, this guy was born 1832 in England, so he was British. What else do we know? He went to Christ Church College of the Oxford University back in 1851. He done mathematics. He was actually a mathematician. We all know him for the books that he wrote, or Alice in Wonderland, but he was actually a mathematician. More than that, he was a logician. So he was interested in logic equations, which is what we will be dealing with here. In 1855, he became a lecturer for mathematics in Oxford University. But he had other hobbies. He actually liked drawing, he liked theater, but he wasn't actually really good at it. He tried to submit some of his drawing to some magazines, and they told him, no, you crap. So he took photography instead. And that was before he even became an author. So he took some photography, and he actually was really good at it. And started making it into a bit of a business. Now he only got into writing stuff. He was always sort of like a little bit of a writer. But back in, let me check when, 1856, there was a new dean of the college he was lecturing at, and he became really friendly with the dean and his family. With the dean's wife, and they had 4 kids, 1 boy and 3 little girls. He was especially friendly with the 3 little girls. And they went on sailing trips and had a bit of fun. One of the girls was actually Alice. And then one day when they went sailing, he wrote her a story, which later became Alice in Wonderland in later editions. Someone saw the story and thought it was great and sent it for publication, and the rest is history. Now, the thing with him, so he was many great things. He was an author. He was actually a pretty good mathematician, pretty good photographer, but he did like to mess with the little girls every once in a while. There's rumors, strong rumors that said he was a pedophile, although it was never actually been proved. So, you know, rumors being rumors. Some say he used to take a lot of pictures of small girls just because he was part of the era and that's what people used to do. Other people say he was purely a pedophile. Read what you want into it. Anyway, so that's a very interesting character. By the way, speaking of this one, can anyone make sense out of it? How can we make this statement be true? Huh?
We have no positional.
No, it's in positional.
He gets that he's just adding 12 and 13, so he's saying that 4 and 7 will be 14 by his life.
No,
4 times 5
that
is 12, then he's saying 4 times 6 is 13.
yeah.
And for the next number, he would say 4 times 7 is 20.
Is 20? No, but we'll never get to 20 at this rate.
So he's increasing what by
It's a bit of a puzzle. What would be the next one in the series? How much is maybe 14? Well, this would actually be true if we worked in base 18 here. So 4 times 7 in decimal will give you 20. If you work in base 18, it'll give you 12. Same logic if you go and you look at 4 times 6 in base 21, you will get 13. And if we continue this logic on 4 times 7, well, the next base will be 24. And you can probably figure out what this will be. If you continue the trend, by the way, with all the numbers, you will see that you will, in fact, never get to 20. So, you know, that's from Alice in Wonderland. So he did put a lot of mathematical tricks in his writing. If you look for it, I think there's actually a book that points out all these things. Anyway, enough of that. Let's be serious again. So we defined different operations. We said we had the and, the or, and the not. What we will do now with these mathematical operations, Boolean arithmetics, we will implement circuits, because this is what we're here for. It's an electrical engineering course. Now we have 3 symbols for the gates that we will use for those 3 operations. An AND gate looks like this, and if you ever see me draw it, you'll probably end up with something like this. The reason why I'm showing you how I draw things, because you will probably see them and you probably should know what I mean. This AND gate obviously takes 2 inputs, x and y, and throws out x and y, which corresponds to how we defined AND. Similarly, there's the OR gate, which always mess up. Which will, for 2 inputs, x and y, we'll throw out x or y. And then we have the NOT gate, usually called an inverter, that, as we said, takes only 1 input, throw out the complement of this input. And that's an easy one to draw there. I think the trickiest one is the OR gate that I always get wrong. Now, we will usually deal with electrical signals in using waveforms. Now, because we only have 2 values, zeros and ones, waveforms will take one of 2 values, a 0 value and a 1 value. And then if we want to show how the 3 gates look in terms of waveforms, we will have the waveform for x and for y. And you can verify that we cover all 4 different combinations, 0, 0, 0, 1, 1, 0, and 1, 1. And therefore, the outputs of the gates will be, for the end, we said for anything that has a 0, we'll get a 0 at the output. If both of them are 1, we'll get a 1. Therefore, this kind of waveform. Similarly, for an OR gate, if both of them are 0, we'll get a 0. If at least 1, we'll get a 1. And note x is the inversion of the x waveform. Now, a lot of times you'll hear us, in terms of waveforms, talk about high and low voltages. So, very obviously, low voltage will correspond to a 0, and a high voltage will correspond to a 1. So we either talk about low and highs or 1s and 0s. Now, what I don't actually show you in this waveform here, in this I'm actually assuming that our electric gates are very ideal. So as soon as inputs come in of some sort, or as soon as they change, the output changes with them. In real life, this is not always the case. Actually, it's never the case. We do have some kind of a propagation delay through the logic gate. So, for example, if I, this would actually be the waveform for a buffer. Buffer, by the way, we'll talk about later in the course. It's a gate that on the surface of things doesn't do much. It just outputs the same signal. They do come in useful, we'll talk about it. But it does experience that gate delay that I was telling you about. And you can see that once the input changes, the output changes sometimes afterward, denoted as TG, gate delay. In this example here, the gate delay will be 0.3 of a nanosecond. So those gate delays are fairly short. We are talking about nanoseconds or sub-nanoseconds. But when we have really, really high-speed circuits, those things are things we must take into account. Now, it also matters. That's, for example, an OR gate with two inputs A and B, output C. As we said, once one of those inputs change and the output needs to change, it will take some propagation delay through the gate for the output to show up. It does actually matter which input change. Suppose we start with A and B being both 1, 1. We might actually get different gate delays if the A changes its value from 1 to 0, or if it's the B that changes its value from 1 to 0. One of them, for example's sake, might be 0.3 nanosecond. The other one might be 0.5 seconds, nanoseconds. And not all gates have the same propagation delay. It depends a lot on the technology which we use. There's different technologies to use to implement logic gates. So there's all these things that come into account. Usually when we talk about a general gate delay, TG number, it's usually there to give you some figure of what's either the slowest possible change. So it might actually calculate which input change will produce the slowest output change, and will give you that as the gate delay. Or this might be the average of all the different gate delays. But it does give you some figure, and obviously a data sheet for a gate will tell you what this number stands for. But it gives you some good sense of the speeds you can work with this gate. Now in this course, we will not cover too much of delays through gates. We will usually assume that our gates are ideal, that the outputs change as soon as the inputs change. And this is how our waveforms will look like, instantaneous change. In your lab, you will usually simulate your circuits on the computer, assuming, again, ideal gates. So you will see the change happens instantaneously. Although you can set your simulators to simulate more realistic circuits, and this will take into account what technology you're implementing it on. If you download it on some development board, it will ask you what board is it or what chip you're downloading it to, and it will be able to simulate the correct propagation delays. And then once you know your propagation delays, you can figure out how quickly we can run the circuit. If you have a computer, for example, actually, in fact, let's talk about this. Why are we limited by the clock speed of your home PCs? I think these days the really fast ones run at 3 gigahertz, or anybody knows better, maybe a bit faster than that. So we talk about clock speed that's 3 gigahertz on home computers. Now, what prevents us from actually going to 4 gigahertz? The quicker the clock is, the faster we can do operations. Yes, Deacon?
Mainly that they get too hot once they're running too quickly.
They do get hot. They consume more power. The quicker they run, the more power they consume, and the hotter they get. But that's not the reason, because we can cool them using different methods. These days they have liquid cooling, which is actually pretty cool. But it's not. By the way, we bought a server just last week. We had to choose between 2 servers. One had liquid cooling, the other one didn't. We only did liquid cooling just for the coolness of it. True story. Anyway, but it's not because they get too hot. We can deal with heat. Not so much with laptops. Laptops, heat problem is a bit larger, but it's not because of the heat. Any other reasons in relation to what we just talked about?
Speed of the electron.
Eh?
Speed of the electron.
Speed of the electron, or in other words, gate delays. Yeah, it takes some time. When you do an operation on one side of the gate, it takes some time for the output to stabilize to the right value. If you clock the gate too quickly and you put new inputs into the gate too soon, you won't get the correct output from the previous operation. And this is what limits us with the clock speeds. There's always an ongoing research about finding quicker technology. Obviously, the smaller you make your transistors as generations go, there's less path for the electrons to go through, and therefore we can actually speed up our computers. So part of the reason why we're able to go to quicker computers from what we could 10 years ago and 20 years ago is because our parts are literally or realistically smaller. There's less path to travel and less other things, capacitances and resistances in the transistors, and we can run the gates faster. But now we have a problem. We almost at the limit of how small we can make transistors. That's a whole different story. So we might actually start standing still unless some new technology comes about. Anyway, I talked about representing functions using a truth table. I said we can write the different combinations of our inputs and then come up with a function, values for the function. This is, again, some arbitrary function that came from somewhere. And it actually corresponds to this Boolean equation. The function equals x or not y and z. And then if you take each combination, you put the right values into your equation, you get the value for the function. So for example's sake, let's take the first row, 0, 0, 0. If this is 0, not y is 1, z is 0, 0 and 1 will give us a 0, or the other 0, the function becomes 0. And you can verify the other ones, the other function values. Now in terms of logic diagram, this corresponds to the equation that I wrote up there. So you have your x, y, and z inputs. X is ORed with whatever block we have here, which gives us the not, y, and the z ended together to the input of your OR gate. Now, for any given function, there's only one unique truth table that will represent this function. However, I can write the same function using different expressions, and I can implement it using different logic diagrams. Just to show you sort of a general case, which might be obvious, but it sort of proves this point. What if I add 2 more inverters at the end of this function? It's a different logic diagram. I have more elements in it, more gates, but I will get this very same output. And by the way, if I want to write it in the equation, I will just negate the whole thing and then negate it again, which is what I've done here. My truth table doesn't change. So truth tables are unique. Equations and logic diagrams are not. Questions so far? By the way, some of this might look fairly simple. It might look like, yeah, it makes sense, no problems. The only reason why I want to go through it and formalize everything is once we start working on slightly more complex equations and more complex circuits, we will need to go back to the definitions and remember all of these things. That's why I'm sort of going through it. I'm going through it slowly, and that's why you need to know it. So I mentioned Boolean algebra quite a few times. What is a Boolean expression? It's an algebraic expression made of, what do we have? The binary variables, so the letters could be letters or words, made of the constants 0 and 1, which are perfectly good binary values. The logic operation symbols, which are the plus symbol, the multiplication symbol, and the overbar, stands for and or not, and parentheses to determine the order of execution of the expression. Now with those operations, the parenthesis always takes precedence, followed by a not operation, followed by an and, followed by an or. It's sort of very similar to what we do in mathematics anyway, so it makes sense. You don't have to memorize anything new. Let's take an example of some Boolean expression. This is a perfectly good Boolean expression. The order of operation that we'll go about doing this, first of all, the parenthesis. So we will evaluate not A plus B for any combination of A, B, C, and D. Then the result from here will be ended with C. D and 1, by the way, will always give us a 1 because anything and 1 will give us, sorry, D and 1 will always give us D because anything and 1 will give us the same thing. And we will talk about the identities in a second. And then once we evaluated this part and this part, we OR them together to get the result. Now in this case, I usually used the operation only on one variable, but I can do things like which is something I've done in the previous slide. I can negate a whole expression. Now we said the invert operation is a unary operation. It only works on one variable. But you can see that if I wrote it in another notation, with the dash notation, you can now see that what I'm really doing is I'm evaluating x or y and then negating the whole thing. And it's quite clear once I put the overbar on top of the whole expression. Now, do you know who came up with Boolean algebra? This guy. Still not De Morgan. Someone else. Although De Morgan was his friend. Well, friend is a, it's a big word. They were acquaintances. They worked together. De Morgan, by the way, was slightly older than him. Anybody knows anything about George Boole? Anyone heard about George Boole before coming here? You know George? Different George? Ah, different George. There's George Bush? No. No, so this guy, so I looked him up a little bit, and what I found, he was English as well. He was born in 1815, which is way before, not way before, but it was before Lewis Carroll. Was this a question or? No, you're right. Not you, your friend. Anyway. Now this guy, according to my searches, was born to a very poor family. And when he was a kid and he wanted to study, he couldn't afford a lot of books, and at the times math books were not so much more available, but you needed really less math books in order to learn a subject, rather than if you bought books about laws or poetry. So it made it more economically viable for him to buy the math books. Also, you can actually make more money being a mathematician. So he decided to take mathematics. And he was actually pretty good at it because, you know, he was poor, he was sitting at home learning math. When he was 16, he started helping out in some school. He was the deputy principal. And then when he was only 19, he decided to open his own school. And he started teaching some high school students. What else do I know? So he was actually very interested in logic mathematics, so things like the stuff that we'll do here. By the way, have you guys done discrete math in first year or at any point in your degree? No? They used to, part of electrical engineering used to be discrete math in first year. I suspected they took it out of the program, which is a shame. In discrete math, by the way, you learn about all about formal logic, and it's not quite Boolean algebra, but it's logic, not equations, but logic formulas and logic deductions. The kind of things I think you see in your SATs if you're from America, I think. Yeah? No?
Just American, sorry.
Okay. Anyway, back to this George Boole. So he was all interested in logic. What else do we know about it? He started publishing an article about logic, but and he came up with the whole theory of Boolean algebra that was later called after his name. But his publications did not really make any impact on anyone. And only until it was 15 years after he died that someone picked up his transcripts and thought, oh my god, this guy was a genius, let's work with it, and then developed what was later known as Boolean algebra. So we do owe it to him. By the way, he died fairly young, I think when he was 49 or 39? 49. He had some severe case of fever or something, so that's a shame. So that's about George Boole. Let's take a break now for 10 minutes, and we'll continue then.